Hello, everyone. Welcome to the Cybernetters Networking 1 course. I'm Andrew Yick, and today we're going to dive into an essential aspect of networking, which is cabling and media. So, in this presentation, we'll focus on the different types of physical media used to connect devices and keep our networks running smoothly. We'll primarily cover copper and fiber optic cables, and we'll explore the characteristics, uses, and why choosing the right cable is so important for network performance. Before we go deeper into the different types of cables and whatnot, let's take a look at the a few IEEE standards. So basically, the physical layer has a bunch of standards that needs to be followed, which is governed by the Institute of Electrical and Electronic Engineers, which are also known as IEEE, which defines the standards for many LAN protocols. So we can see stuff like 802.2, which is the logical link control, 802.3, which is Ethernet, which we'll be discussing in a later video, and 802.11, which is wireless. These standards help ensure compatibility and reliable communication across different network systems and printers. So now that we have seen how IE defines standards for various network protocols, they're not really the only thing that shapes how we build networks. Another aspect of the physical layer involves the TIA and the EIA. So instead of focusing on network protocols, these focus on structured voice and data wiring. Their standards cover everything from twisted pair cabling and telecommunications pathways, which is all important for maintaining reliable and scalable network infrastructure. So, as we mentioned in the last video, bandwidth is basically how much data can be transmitted over a network. So let's go over the units of bandwidth. So the units of bandwidth we have is BPS, KBPS, MBPS, GBPS, and TBPS, which is shown in the table there. So you might be wondering, why does it even matter? Faster bandwidth means you can transfer or transmit more data between networks, which could help with online gaming, cloud computing, or video streaming because you would want faster data rates for that. Let's go over the different types of speed. So bits per second is like the fundamental unit of bandwidth. Kilobits per second is basically 1,000 bits per second or 10 to the third bits per second. Megabits is a million bits per second or 10 to the sixth. Gigabits is a billion bits per second or 10 to the ninth bits per second. And terabits is a trillion bits per second or 10 to the 12 bits per second. So the first type of cabling that we will talk about is the copper media, which is basically used to connect network devices. It transmits data using electrical signals. So as you can see in the image, we have the different types of copper media, which one of them is the coaxial cable, which is the top image, which has a central conductor, which is surrounded by insulation shielding and an outer sheath. It is more used in cable TV and older Ethernet networks. And then we also have the UTP cable and the RJ45 connections, which we'll go in depth about later in the video. So standards ensure compatibility and reliability across devices and networks. So some common standards for copper cables are the cable types, which can come in Cat5e, Cat6, Cat6A, and Cat7. For the bandwidth capabilities, Cat5e can go up to 1 gigabits per second, Cat6 can go up to 1 gigabits per second or 10 gigabits for short runs, and Cat6As can go up to 10 gigabits per second. For connectors, we have the RJ45 for Ethernet and then the F-type connectors for Coaxial cables. For the pinouts, we have the T568A and the T568B, which define the color coding of the twisted pair cables, which we'll be going more in depth later in this video. Copper cables can have distance limitations due to signal degradation, which is basically when it experiences a loss of signal quality or strength as it travels from a transmitter to a receiver. Some pros and cons of copper media are that they're cheaper than fiber optics, they're flexible and easy to maintain, and they're widely supported. Some cons are there's EMI interference from other nearby devices or equipment, and then there's crosstalk, especially in UTP cables. And then there's distance limitations. Basically, anything beyond 100 meters requires the fiber optic cables. Let's now dive deeper into unshielded twisted pair cables, otherwise known as UTP. So what it does, it's basically a bunch of copper wires that are twisted together in order to limit signal interference. So it is made of three parts, as you can see in the diagram. So first, you have the outer jacket, which its main job is to prevent it from being damaged physically, like accidentally like cutting it or something like that. The twisted pair is basically what I was talking about the twisted copper wires. The main point of that is to prevent protect the signal from interference. And then you have the color-coded plastic installation, which basically electrically isolates wires from each other and identifies each pair. So you can see how each color is separated from each other. So for the UTP cables, there are TIA and EIA standards. So there are the cable types, there are the cable lengths, the connectors, the cable terminations, and there's the methods of testing. The IEEE also assigns categories using the bandwidth performance. So Cat 5 can have a slower performance, and then Cat 6 can have the highest performance. So for the copper media, there are two different standard wiring patterns, as you can see in the diagram. They're called the T568A and the T568B. So imagine you're driving on a one-way highway where all lanes go into the same direction from point A to point B. Each car represents a signal, and the highway ensures smooth travel to the destination. So in this case, in a straight-through cable, the wiring inside follows the same order on both ends, which allows data to travel in a direct, predictable path between two different types of devices, such as PC to switch or a router to switch. So now imagine two roads meeting at an intersection with a traffic light. Cars on one road need to switch lanes to the other side to continue their journey in the opposite direction. This makes sure that both lanes can send and receive traffic smoothly. So in a crossover cable, the transmit and received wires are swapped at one end, which allows two similar devices, like a PC to a PC or a switch to a switch or even a router to a switch, to communicate directly. Without this lane switch, so-called lane switch, both devices would be talking on the same lane and not hearing each other. Rollover cables are primarily used for Cisco networking devices. So it is used to connect a workstation serial port to a Cisco's device's console port for configuration. Since many PCs no longer have serial ports, a USB to serial adapter is often needed. Also, T568A and T568B may be used, but since the cable is reversed, it does not function like straight-through or crossover cables because these rollover cables are only used for console access and device management. We also have a Coaxial cable, which is a shielded copper cable used for high-frequency signals. It is able to run longer distances than STP or UTP. It consists of an outer jacket, a braided copper shielding, a copper conductor, and a plastic insulation. We also have the shielded twisted pairs, also known as STP. STP cable shields the entire bundle of wires within the cables as well as the individual wire pairs to provide better noise protection than UTP. Let's now talk about how fiber optic cables compare to copper cables. So, fiber is more expensive than copper for the same distance, but it offers higher bandwidth and speed. Fiber requires specialized skills for equipment for splicing, terminating, and repairing, while copper is easier to install and maintain. Fiber is fragile and must be handled with care to avoid bending or breaking, and copper is more physically robust. Fiber is immune to EMI but because it uses light signals instead of electrical signals. Copper is more susceptible to EMI, which can cause data loss in noisy environments. Fiber can transmit over kilometers without signal degradation. Copper has a shorter range before signal loss occurs. The image on the left shows the fiber optic cable structure. So there's the core, which is the glass and plastic fiber, the cladding, the buffer, and the outer jacket. Fiber uses light transmission instead of electricity, which the copper uses. So the right image shows the copper cable structure, which is the shielded twisted pair, and it contains braided shielding, twisted pairs, and foil shield for EMI protection. It uses electrical signals to transmit data. So you might be wondering, when should I use what? So what I would use is I would use fiber when high speed, long distances, and EMI resistance are needed. So for example, the internet backbone, data centers, and WAN links. I would use copper when cost is a factor and short distances are sufficient. So for example, like home networks and office LANs. If you're having trouble remembering what fiber and copper is, what I would do is I would compare fiber optic to a high-speed expressway where cars or data can travel at extremely high speeds without interference or slowdowns. High-speed expressways are best for long distances like between cities and across states, and they're more expensive to build. And I would also think of copper cables as local streets and roads. Copper is like the local city streets with stop signs and traffic lights. Cars or data can travel efficiently, but traffic congestion, which is EMI in this case, and speed limits slow things down. It is limited to shorter distances, like if you want to get from like your house to school, and it is cheaper and easier to build for shorter connections. Let's talk about how fiber optic cables are constructed and how they enable full duplex communications. So, as we talked about earlier, fiber optic cables uses light signals to transmit data, and they're built within multiple data to protect and maintain signal integrity. So you first have the PVC jacket, which is the outer protective layer that prevents physical damage to the fiber. And then you have the strengthening materials, such as amarid yarn, which protects the delicate fiber core from bending and breaking. There's cladding, which is the layer surrounding the glass or plastic fiber, which is designed to reflect light back into the core, preventing signal loss. Since, as I said earlier, fiber optic cable uses light signals to transmit data. And then you have the fiber core, which is the actual glass or plastic strand where data travels in the form of light pulses. Thank you so much for watching. If you have made it this far, I truly appreciate your time and attention. If you found this video helpful, don't forget to give it a thumbs up and feel free to subscribe for more content like this. Do you have any questions or feedback? Drop them in the comments. I'd love to hear from you. Until next time, keep learning, stay secure, and I'll see you in the next video. Bye bye.